72 hours ago, the European Space Agency released what they promised would be the clearest image yet of 3I/Atlas, the mysterious interstellar visitor that's been simultaneously captivating and terrifying researchers around the globe. Billions of dollars in cutting-edge space technology. 7 different Mars orbiters positioned for what should have been the photograph of the decade. And what did humanity receive? A blurry white smudge that resembles someone's fingerprint on a foggy window. Within moments, social media platforms ignited not with scientific wonder, but with fury. Amateur astronomers operating simple backyard telescopes were capturing sharper images of comets located millions of miles farther into deep space. Meanwhile, NASA, with its Mars Reconnaissance Orbiter equipped with the most sophisticated camera ever deployed to another planet, has maintained absolute radio silence. The government shutdown explanation is wearing dangerously thin, especially when we realize that Chinese and UAE orbiters have also gone mysteriously quiet. By the time this narrative concludes, 3I/Atlas will be mere days from vanishing behind our sun, hidden from every telescope on Earth during what should represent its most scientifically significant moment. And if Harvard physicist Avi Loeb's calculations prove accurate, what unfolds next could fundamentally transform everything humanity thought it understood about what's genuinely possible in our cosmic neighborhood. Before we dive deeper into this unfolding mystery, I need your help to keep this investigation alive. Understanding complex scientific content like this requires time and resources. If this content resonates with you, please hit that like button right now. It genuinely helps this video reach more people who are searching for answers. Subscribe to this channel so you never miss updates as this story develops in real time, because I promise you what's coming will challenge everything. Drop a comment below telling me where you're watching from, what time it is in your location, and most importantly, whether you believe we're receiving the complete truth about 3I/Atlas. Your engagement matters more than you realize. October 7th and 8th, 2025 will be permanently etched in history as the precise moment when the global space community collectively exhausted its patience. For months, anticipation had been intensifying. 3I/Atlas, representing only the third confirmed interstellar object ever detected passing through our solar system, was executing its closest approach to Mars. 7 distinct spacecraft from 4 separate space agencies had positioned themselves to capture unprecedented imagery. The expectations were legitimate. Scientists had promised clarity, definitive answers, potentially even conclusive proof regarding the true nature of this enigmatic object. Then the photographs arrived. The European Space Agency's ExoMars Trace Gas Orbiter, strategically positioned merely 30 million kilometers from 3I/Atlas during its closest approach on October 3rd, released a sequence of images that can only be characterized as profoundly disappointing. A fuzzy white dot drifting slowly across a star field. 0 structural detail, 0 defining characteristics, absolutely nothing that would help humanity comprehend whether we're observing a natural comet or something far more extraordinary. The public backlash erupted immediately and viciously. Astronomy Vibes, a prominent space commentary account on social media, published a side-by-side comparison that achieved viral status within hours. On one side, a remarkably crisp, detailed photograph of Comet Lemon captured by an amateur astrophotographer using nothing more sophisticated than a consumer-grade mirrorless camera. On the opposite side, the ESA's image of 3I/Atlas. The caption posed a devastating question that resonated with millions. If a simple mirrorless camera can capture Comet Lemon with such clarity, why can't NASA capture 3I/Atlas passing close to Mars? The post currently exceeds 40,000 reposts and continues climbing. But the follow-up commentary truly struck a nerve with the scientific community. Billions in funding, and this represents the best photograph they can produce? It resembles a weather balloon photographed in someone's foggy backyard. To genuinely comprehend why people are experiencing such frustration, we need to understand the massive disconnect between expectations and delivery. The CASIS camera aboard the ExoMars Trace Gas Orbiter possesses an angular resolution of 11.36 microradians per pixel. At 30 million kilometers distance, that specification translates to approximately 340 kilometers per pixel. For critical context, the estimated nucleus of 3I/Atlas measures somewhere between 5 and 46 kilometers across. That mathematical reality means the entire solid core of this object would occupy, at absolute best, a minuscule fraction of a single pixel in these released images. Here's where the situation becomes genuinely intriguing. The ESA understood these limitations from the beginning. They knew with absolute certainty that their cameras were engineered to photograph Mars's bright surface from merely a few hundred kilometers away, not faint objects tens of millions of kilometers distant in deep space. Nick Thomas, the principal investigator for the CASIS camera system, acknowledged this limitation in the official statement released alongside the images. This represented an exceptionally challenging observation for the instrument. The comet is approximately 10,000 to 100,000 times fainter than our usual observational target. So why release images they knew categorically would prove inadequate? Why construct expectations for months only to deliver something providing zero new scientific information? The official explanation suggests they released what data they possessed, that these images represent the absolute best possible captures from the available equipment. However, the timing feels deliberately calculated, almost resembling a pressure release valve. Provide the public something, anything, to examine while the genuinely significant data remains locked away in classified databases. Because make absolutely no mistake about this crucial fact. Superior images exist. Far superior images. And they're being deliberately withheld from public disclosure. While the European Space Agency distributed fuzzy dots to satisfy public curiosity, NASA's Mars Reconnaissance Orbiter was capturing something entirely different. The HiRISE camera, an acronym for High Resolution Imaging Science Experiment, represents the most powerful imaging system ever transmitted to another planet. Its resolution capacity is so extraordinarily precise that from Martian orbit, it can distinguish objects the approximate size of a kitchen table on the planet's surface. When 3I/Atlas executed its closest approach to Mars on October 3, HiRISE possessed a resolution of approximately 30 kilometers per pixel at the object's distance. That specification delivers more than 10 times superior resolution compared to what the ESA cameras achieved. If any structural anomalies exist, any unusual geometric features, anything whatsoever that doesn't conform to the natural comet narrative, HiRISE would have detected it with absolute certainty. Avi Loeb, the Harvard physicist who's been meticulously tracking 3I/Atlas since its initial discovery, articulated the situation bluntly in his latest blog publication. The brightest pixel in the HiRISE image will provide the best constraint yet on the actual area of 3I/Atlas. We are all desperately hoping that the HiRISE team will release their images as expeditiously as possible. That statement was published on October 7th. Multiple days have elapsed. Still absolutely nothing. The official explanation continues to be the United States government shutdown. Over 15,000 NASA employees, representing more than 80% of the agency's entire workforce, have been furloughed indefinitely. NASA's official website isn't receiving updates. Public communications have completely ceased. It represents bureaucratic paralysis manifesting at the absolute worst possible moment in recent astronomical history. But here's the critical detail that doesn't logically reconcile. The ESA released their images without difficulty. They represent a European agency completely unaffected by American political dysfunction. China's Tianwen-1 orbiter was similarly positioned to observe 3I/Atlas with its moderate-resolution imaging camera, also maintaining complete silence. The UAE's Hope orbiter, equipped with the Emirates Exploration Imager, possessed an unobstructed shot as well. Nothing released. Multiple space agencies, multiple sovereign governments with completely independent bureaucracies and competing national priorities, all simultaneously unable or deliberately unwilling to release their optimal data on the most scientifically significant object to visit our solar system in years. The pattern becomes increasingly difficult to dismiss as mere coincidence. If you're still watching, you're exactly the kind of person who deserves to know what's really happening. Before we continue, let me ask you something directly. Do you think this silence is accidental? Comment below with your honest opinion. And if you haven't already, smash that subscribe button because what I'm about to reveal next will challenge everything mainstream science has told us. Social media platforms are ablaze with increasingly sophisticated speculation. Some observers suggest coordination between agencies. Others propose that something was photographed that requires exceptionally careful review before public release. The more conspiracy-minded researchers suggest the images reveal something so profoundly anomalous that releasing them without extensive contextual preparation would trigger mass panic across global populations. That final theory sounds absurd and easily dismissible until we remember what's been transpiring over the past week with amateur observations. Because while professional space agencies have remained cryptic with their superior data, backyard astronomers have been capturing images that generate more questions than they conclusively answer. On October 3rd, the exact day 3I/Atlas executed its closest approach to Mars, a Portuguese amateur astronomer operating under the username Dobsonian Power uploaded an image that immediately achieved viral distribution across every major astronomy platform. Using nothing more sophisticated than a solar telescope from his residential backyard and some aggressive digital enhancement techniques, he captured what appears to be angular structures within 3I/Atlas. Dark geometric shapes, distinct protrusions that don't match the typical diffuse glow characteristic of a comet's coma. The caption he added was simple but loaded with profound implication. What on earth is it? Within 6 hours, the image had been disseminated across every major astronomy forum, subreddit, and social media platform imaginable. The reaction split into two opposing camps almost instantaneously. One group observed clear evidence of artificial structures, definitive proof that 3I/Atlas is categorically not what mainstream science claims it to be. The opposing group dismissed it as classic pareidolia, the well-documented human tendency to perceive meaningful patterns where none genuinely exist, amplified by processing artifacts from inappropriate equipment usage. The debunkers presented solid technical arguments supporting their position. Solar telescopes utilize specialized filters engineered specifically for observing the sun's extreme brightness, not faint deep space objects traveling at interstellar velocities. The equipment simply wasn't constructed for this type of observation. Add aggressive digital enhancement to compensate for inadequate setup, and you're essentially requesting an algorithm to manufacture details that aren't authentically present. It represents the astronomical equivalent of enhancing a blurry photograph until you start perceiving faces in random noise. However, here's where this story becomes genuinely complicated. Dobsonian Power isn't some random internet conspiracy theorist possessing a cheap telescope and excessive imagination. He represents a respected amateur astronomer who's been sharing legitimate astrophotography work for over a decade. His YouTube channel features meticulous documentation of his equipment specifications, his methodological approaches, his complete image processing workflows. This isn't someone attempting to manufacture fraudulent evidence for clicks and monetization. And when pressed regarding the anomalous structures visible in his 3I/Atlas image, he didn't double down with wild, unsubstantiated claims. Instead, he acknowledged uncertainty with scientific humility. He promised to attempt observation again when the object becomes visible from Earth in early November after passing behind the Sun. His response was measured, scientific, appropriately cautious, which makes the aggressive reaction to his image even more revealing. Within 24 hours of the initial posting, Multiple websites published articles specifically debunking his capture with remarkable speed. Amateur telescope captures strange 3I/Atlas image. Here's why it's not what it seems. The timing felt coordinated. The tone felt defensively aggressive, as if someone needed to rapidly establish the narrative that nothing unusual had been photographed, that any apparent anomalies were merely technical artifacts, before the image could gain excessive traction in public consciousness. And then the enhancement wars commenced in earnest. Users across Reddit, Twitter, and various conspiracy forums started downloading the original ESA images and processing them through their own sophisticated algorithms. Some employed standard astronomical image stacking techniques developed over decades. Others utilized AI upscaling tools designed for enhancing low-resolution photographs. A few went completely chaotic with machine learning models trained specifically to reconstruct fine details from severely limited data. The results varied wildly across the spectrum. Some processing revealed nothing except slightly sharper versions of the identical fuzzy dot. Others revealed what appear to be distinct geometric patterns, defined edges, structures that seem excessively regular to represent natural ice and rock formations. The fundamental problem emerges when you start aggressively processing an image, especially with AI tools. You're no longer examining what's actually present in the original data. You're examining what an algorithm thinks should be present based on its training data parameters. If you train an AI system on thousands of images depicting spacecraft and then request it to enhance a blurry dot, it might very well invent spacecraft-like details because that's precisely what it's been programmed to recognize through machine learning. It represents a scientific dead end wrapped in the seductive illusion of enhanced clarity. However, the proliferation of these enhanced images generated an unintended secondary effect. They muddied the informational water so thoroughly that distinguishing between legitimate amateur observations and outright digital fabrications became nearly impossible for average viewers. Within 48 hours of the ESA photo release, there were dozens of supposedly enhanced versions circulating online through various channels. Some displayed metallic surfaces with reflective properties. Others depicted what resembled solar panels or antenna arrays with suspicious geometric precision. A few even included what appeared to be running lights and visible thruster systems. Most were obviously fraudulent, digital art created by individuals with excessive time and sophisticated Photoshop skills. But mixed strategically within this noise were a handful of images that felt qualitatively different, more subtle in their claims, less sensational in their presentation. Images that displayed just enough unusual regularity to make careful observers genuinely wonder whether something authentic was being deliberately obscured by the manufactured flood of obvious hoaxes. If you've made it this far, you're clearly invested in understanding the truth. That means everything to me. Take a moment right now to leave a like on this video. It tells the algorithm that this content matters, that people care about real investigations, not just entertainment. And comment below with your thoughts so far. Do these patterns seem suspicious to you? Or am I connecting dots that don't exist? Your perspective matters. On October 4th, an anonymous user on 4chan's paranormal board published what they claimed represented insider information about 3I/Atlas. The post was titled simply ESA Data Leak, and it commenced with a credential claim that was specific enough to sound potentially legitimate but vague enough to maintain complete anonymity. I am a doctoral researcher working with the European Space Agency with continuous access to the combined observational data of 3I/Atlas. Internet leaks are extraordinarily common, worth practically nothing. Most are easily dismissed as creative fiction or outright trolling designed to provoke reactions. But this particular post was qualitatively different from typical anonymous claims. The level of technical detail was genuinely unsettling for those familiar with the science. The poster didn't make wild, unsubstantiated claims about alien invasions or secret military operations against extraterrestrial craft. Instead, They methodically laid out a series of specific observational anomalies that, if authentic, would fundamentally challenge our understanding of what 3I/Atlas actually represents. The first anomaly identified: chemical impossibility. According to the detailed post, spectroscopic analysis demonstrates 3I/Atlas is releasing approximately 100 kilograms of nickel gas per second, but with almost no corresponding iron emission whatsoever. In normal stellar and planetary chemistry throughout the known universe, nickel and iron are inseparable twins. They form together in supernova explosions. They travel together through interstellar space for billions of years. And they appear together in comets and asteroids without exception. Finding abundant nickel with virtually no iron violates basic assumptions about how matter behaves in natural cosmic environments. It's analogous to finding smoke without any corresponding fire. It contradicts fundamental chemistry. The second anomaly described: thermal contradiction. The object is releasing massive quantities of gas and dust, representing the characteristic signature of an active comet being heated by solar radiation, yet infrared observations demonstrate it remains cold, far colder than physical models predict it should be given its outgassing rate and proximity to solar radiation. The poster compared it to observing someone sweating profusely while standing in a freezer. The physics don't match the observation in any conventional model. The third anomaly presented: trajectory precision. The post referenced what Avi Loeb has been stating publicly, that 3I/Atlas arrived with an orbital inclination of just 4.89 degrees relative to Earth's ecliptic plane. But the 4chan poster added critical context Loeb didn't emphasize in public statements. The trajectory isn't merely unusual from a statistical perspective. It represents a perfect straight shot from the precise direction of the galactic core. No wobble detectable. No deviation from a straight path. No observable signs of gravitational perturbation from nearby stars during its millions or potentially billions of years traveling through interstellar space. As if it was deliberately aimed at our solar system. Then arrived the section that elevated this from interesting speculation to something considerably darker and more concerning. The poster claimed the object fits the profile of what they termed a post-biological entity. Not a natural comet formed through accretion. Not a conventional spacecraft constructed from metal and propellants. Something existing in between these categories. They described it as possessing a three-phase particle engine, with an estimated continuous power output of 75 megawatts, continuously transmitting an active signal into space, and in their precise words, probing our solar system with intent. The post concluded with an elaborate theoretical framework. The poster suggested 3I/Atlas might represent a macroscopic quantum object, specifically something called a cue ball. It's an exotic theoretical construct from advanced particle physics, a type of non-topological soliton that could theoretically exist at scales far larger than subatomic particles. If stable configurations exist, a cue ball could possess properties that seem impossible under conventional physics. It could be incredibly dense while appearing diffuse to conventional observation. It could absorb and redistribute energy instantaneously across its entire structure through quantum entanglement, explaining the thermal contradictions observed. It could even explain the nickel without iron problem if the cue ball's internal quantum state preferentially produces certain isotopes through exotic particle interactions. Within 18 hours, the post had been screenshot and shared across Reddit, Twitter, and dedicated UFO research forums with exponentially growing engagement. The conspiracy subreddit thread discussing it accumulated over 2,000 comments before moderators locked it for allegedly violating rules against unverified claims. But locking the thread didn't stop the conversation from propagating. It just fragmented it into dozens of parallel discussions across multiple platforms, each pulling the original post in different interpretive directions. Some focused exclusively on the chemical anomalies. Others zeroed in specifically on the cue ball hypothesis. A few started connecting it systematically to earlier claims about 3I/Atlas potentially being the source of the legendary 1977 WOW signal that has mystified scientists for decades. We're approaching critical information that mainstream media won't touch. If you want to see where this investigation leads, you need to subscribe right now. Click that button. Enable notifications. Because what's coming next connects dots that have been 48 years in the making. On October 4th, NASA's Perseverance rover, sitting in Jezero crater on the Martian surface, captured something unexpected in the night sky above. The image from its right navigation camera displayed an elongated streak of light roughly 4 times longer than its width. At first glance, it resembled a typical long-exposure capture of a moving object. Comets and asteroids frequently appear smeared in images when the camera tracks stars instead of the object itself. Standard photographic behavior. Except the mathematics didn't work out that way upon closer examination. When analysts started calculating the apparent size of the streak based on Perseverance's known camera specifications and the distance to 3I/Atlas at the precise time of capture, they arrived at a profoundly disturbing number: 50,000 kilometers in length. That's not a comet nucleus by any conventional definition. That's not even a comet with an extended tail. That's something else entirely beyond our current classification systems. For critical comparison, Earth's diameter measures less than 13,000 kilometers. If the streak represented the actual physical size of 3I/Atlas, we were observing an object nearly 4 times wider than our entire planet. Social media platforms exploded with increasingly sophisticated speculation. Was 3I/Atlas actually a massive cylindrical craft of artificial origin? Had it been successfully masking its true size and geometric shape this entire time behind a diffuse cloud of gas and dust? The timing felt profoundly significant. This image emerged just 1 day after the Mars flyby, precisely when all professional space agencies went mysteriously quiet. Some observers interpreted it as confirmation that something deeply anomalous had been photographed, something that couldn't be easily explained away through conventional astrophysics. The speculation reached sufficient intensity that Representative Anna Paulina Luna, a member of Congress known for her interest in unexplained aerial phenomena, reached out directly to Avi Loeb for his expert analysis. Consider that development for a moment. A sitting member of the United States House of Representatives felt compelled to contact a Harvard physicist about a photograph from Mars. That's not normal protocol whatsoever. That suggests someone in official channels was concerned enough to want expert interpretation outside the usual NASA communication pipeline. Loeb's response was thorough and, on the surface, reassuring to those seeking conventional explanations. He calculated that the Perseverance navigation camera has an angular resolution of 0.33 milliradians per pixel. At the distance of 3I/Atlas when the image was captured, approximately 38 million kilometers, that translates to about 12,500 kilometers per pixel. The streak in the image spans roughly 4 pixels, which produces that 50,000 kilometer length. But Loeb argued this was an artifact of composite imaging techniques. The streak wasn't displaying the actual physical size of 3I/Atlas. It was showing the path the object traced across the Martian sky during an extended integration time, likely around 10 minutes of stacked exposures. His reasoning was technically solid. Mars orbits the Sun at 24 kilometers per second. 3I/Atlas was traveling at 67 kilometers per second relative to the Sun in the opposite direction, giving it a relative velocity exceeding 90 kilometers per second compared to Mars. Over 10 minutes of exposure, that's exactly 54,000 kilometers of travel, perfectly matching the observed streak length. The shape wasn't representing the object's geometry. It was the object's motion smeared across time in a long-exposure photograph. Case closed. Correct? The cylinder theory debunked by basic physics and careful mathematical analysis. Except Loeb included one sentence in his analysis that conspiracy theorists latched onto like a lifeline. He wrote, "If the navigation camera images represent single snapshots with an exposure time below 3.28 seconds, then the brightness and angular length of the observed source imply that it is not 3I/Atlas. In that case, the source might be much closer to the camera, capable of being smeared into an elongated image with a smaller spatial size and a smaller speed." Wait, process that statement. If these are single-frame captures rather than composites, then what Perseverance photographed wasn't 3I/Atlas at all. It was something else entirely. Something considerably closer to Mars. Something we haven't identified. That qualifier opened a door that no amount of subsequent clarification could fully close, because NASA hasn't confirmed whether the image represents a composite or a single frame. They haven't released the technical metadata. They haven't provided the exposure time or the number of stacked images in the final product. The government shutdown excuse applies here too. No staff available to process public requests. No personnel available to confirm basic technical details about how the image was captured. The silence continues. We're about to discuss something that connects an observation from 1977 to what's happening right now. This is where the story becomes genuinely extraordinary. But first, if this investigation is valuable to you, hit that like button. Seriously, takes 1 second and helps more people discover the truth. And drop a comment telling me if you remember hearing about the wow signal. Let's see how many of you know this history. August 15th, 1977. Ohio State University's Big Ear radio telescope detected a 72-second burst of radio energy so unusual, so perfectly structured, that astronomer Jerry Emmons circled it on the printout and wrote one word in red pen: wow. For nearly 5 decades, that signal has remained one of the greatest unsolved mysteries in the search for extraterrestrial intelligence. It originated from the direction of Sagittarius near the constellation's densest starfields. It was narrowband, focused at one specific frequency, and it has never repeated despite hundreds of follow-up observations. Thousands of hours of listening time pointed at the identical region of sky. Nothing. Just that one burst 48 years ago, and then eternal silence, until Avi Loeb ran the calculations on 3I/Atlas. He calculated precisely where the object was located on August 12, 1977, just 3 days before the wow signal was detected. The answer: approximately 600 astronomical units from Earth, roughly 600 times the distance between Earth and the Sun. But more importantly, he calculated what direction 3I/Atlas was coming from at that specific time. Right ascension 19 hours 25 minutes, declination -27 degrees. The wow signal originated from right ascension 19 hours 25 minutes, declination -27 degrees. The two directions are separated by approximately 9 degrees. In the vastness of space, with random objects arriving from literally any possible direction across the entire celestial sphere, the probability of this alignment is approximately 0.6%. Not impossible, but deeply, profoundly suspicious. Loeb didn't stop his analysis there. He asked the next logical question. If 3I/Atlas transmitted the wow signal from 600 astronomical units away, how powerful would the transmitter need to be? The mathematics is straightforward. The detected intensity was between 54 and 212 Janskys across a 10 kHz bandwidth. At 600 AU distance, that corresponds to a transmitter output between 0.5 gigawatt and 2 gigawatts. For reference, a typical nuclear reactor on Earth produces about 1 gigawatt. So we're discussing nuclear power plant levels of energy focused into a narrow radio beam. Not impossible for an advanced civilization, Actually quite reasonable if you're attempting to send a detectable signal across interstellar distances without wasting energy on omnidirectional broadcasting. There's another detail that makes the connection harder to dismiss as coincidence. The WOW signal was observed at a frequency of 1420.4556 MHz, blue shifted by approximately 10 kilometers per second toward Earth relative to the hydrogen line. That blue shift indicates the source was moving toward us. 3I/Atlas is currently approaching the Sun at about 60 kilometers per second. Loeb suggests that if this object has maneuvering capability, it could have been moving slower in 1977, then accelerated after detecting habitable zone planets in our solar system. A reconnaissance pulse. A radar scan checking for signs of technological civilization before committing to a closer approach. Here's what makes this entire connection so frustrating for researchers. It would be trivially easy to check definitively. Point a radio telescope at 3I/Atlas. Listen at the hydrogen line frequency. If it's transmitting, we'll know within hours. If it's silent, the WOW signal connection is probably coincidental. Simple test. Definitive answer. And yet, as Loeb noted in his latest blog post, not a single radio telescope has reported data on 3I/Atlas. The Very Large Array hasn't looked. The Arecibo telescope is destroyed. The Green Bank telescope hasn't published observations. Even SETI, the organization literally dedicated to finding extraterrestrial signals, hasn't publicly announced any monitoring efforts. The silence from the radio astronomy community is absolutely deafening. The next section reveals statistical impossibilities that mainstream science can't explain. But before we get there, I need you to do something. If you're finding value in this deep investigation, subscribe to this channel right now. Turn on notifications. Share this video with someone who needs to see it. This information deserves to reach as many people as possible. Your action right now determines whether this investigation continues. Imagine throwing a dart at a globe from across a room while blindfolded. Now imagine that dart not only strikes the globe, but lands within a few degrees of the equator. That's roughly the statistical improbability we're confronting when we examine how 3I/Atlas entered our solar system. Objects arriving from interstellar space can theoretically arrive from literally any direction across the entire celestial sphere. They should be randomly distributed, coming in at all possible angles with roughly equal probability. And yet 3I/Atlas arrived with an orbital inclination of just 4.89 degrees relative to Earth's ecliptic plane. Less than 5 degrees. That places it in less than 1% of all possible arrival angles. Avi Loeb has been systematically emphasizing this point in every interview, every blog post, every public statement since July. The trajectory is anomalous, not just unusual. Statistically profoundly unlikely for a random interstellar object passing through. To understand why this matters so significantly, consider how objects move through our galaxy. Stars in the Milky Way disk orbit the galactic center with some average velocity. But they also possess random motions up and down, side to side, like bees swarming around a hive. That randomness means objects ejected from other star systems should arrive at our solar system from all directions with roughly equal probability. There's no preferred direction. No cosmic highway that naturally funnels interstellar visitors into our ecliptic plane. Before someone suggests that perhaps objects from the Milky Way disk naturally arrive at shallow angles due to galactic geometry, Loeb addressed that possibility too. The galactic disk itself is tilted about 60 degrees relative to our solar system's ecliptic plane. 60 degrees. That's more than 10 times larger than the inclination of 3I/Atlas. If this object originated from a typical star system in the galactic disk and was ejected randomly, we'd expect it to arrive at a steep angle, not a shallow one. The alignment is backwards from what galactic geometry would predict. Compare 3I/Atlas to the only other interstellar objects we've detected. Oumuamua, discovered in 2017, arrived with an inclination of 123 degrees. Wildly tilted, coming in from above the solar system plane. 2I/Borisov, spotted in 2019, had an inclination of 44 degrees. Still steep, still consistent with random arrival from interstellar space. Both of those objects behaved exactly as expected for natural interstellar visitors. 3I/Atlas is the outlier, the anomaly, the one that doesn't fit the established pattern. Loeb calculated the probability of this alignment assuming random directions. Less than 1% chance. Some colleagues pushed back, suggesting maybe his statistics were too conservative. Maybe the true probability is closer to 5 or 10% when accounting for various selection effects and observational biases. Fine. Even at 10% probability, you're still examining something that should only happen once in every 10 interstellar objects we detect. And we've only detected 3 total. The odds of the third one being the rare exception rather than the rule are not in favor of coincidence. Now layer that statistical improbability on top of everything else we've discussed. The WOW signal alignment also less than 1% probability. The chemical anomalies with nickel but no iron. The thermal contradictions that defy physics. The missing high-resolution images from multiple space agencies. The government shutdown happening at the exact moment we need NASA most. Any single one of these anomalies could be explained away as coincidence, measurement error, or bureaucratic incompetence. But when you start stacking anomalies, when you start multiplying small probabilities together, the compound improbability becomes exponentially harder to dismiss as mere chance. There's a principle in statistics called the prosecutor's fallacy. It's the mistake of treating multiple independent low-probability events as if they're causally related when they're actually just random coincidences that happen to cluster together. If you flip a coin enough times, eventually you'll get 10 heads in a row. It doesn't mean the coin is rigged. It just means you flipped it enough times for unlikely sequences to occur. Skeptics will argue that's what we're observing with 3I/Atlas. A natural comet that happens to possess several unusual but ultimately explainable properties that coincidentally appeared together in the same object. Unlikely, sure, but not impossible. The counterargument is equally valid. If something walks like a duck, quacks like a duck, swims like a duck, and has duck DNA, at some point you need to seriously consider the possibility that it might actually be a duck. Or in this case, if an object arrives on a statistically unlikely trajectory, shows chemical signatures that don't match natural processes, correlates with a 48-year-old unexplained radio signal, and prompts multiple governments to withhold their best imaging data, maybe it's worth seriously considering that we're not looking at a random chunk of ice and rock from another star system. We're approaching the most critical 72 hours in this entire mystery. What happens next could change everything. But I need to know you're still with me. Drop a like on this video right now if you want to see how this unfolds. Comment below with your prediction. What do you think 3I/Atlas really is? Natural comet, alien probe, or something we don't even have a category for yet? Your engagement keeps this investigation alive. Something disturbing started happening around October 5th. Users across multiple platforms began reporting that their posts about 3I/Atlas were disappearing, not being flagged or marked as misinformation with explanations, actually vanishing from existence. A Reddit user documented posting a detailed thread analyzing the chemical anomalies from the alleged ESA leak. The thread gained legitimate traction, accumulated hundreds of upvotes, and dozens of substantive comments within 2 hours. Then it was gone. Not removed with a moderator explanation. Just deleted from existence. When the user attempted to repost, the submission wouldn't process. Shadow banned without notification or explanation. On Twitter, now called X, several accounts noticed similar suppression patterns. Astronomy Vibes, the account that went viral criticizing the ESA photos, reported significant engagement drops after October 7th. Posts that would normally reach tens of thousands of people were suddenly plateauing at a few hundred views. No official restrictions. No warning messages. Just algorithmic suppression. Quiet enough to be deniable, but aggressive enough to be unmistakably effective. Other creators in the space and astronomy community noticed identical patterns. Videos about 3i/Atlas that would typically perform well were getting a fraction of their usual reach. YouTube presented a different suppression problem. Content creators who posted analysis videos speculating about 3i/Atlas began receiving demonetization notices with remarkable speed. The stated reasons varied. Some were flagged for discussing sensitive topics without proper context. Others were categorized as potentially misleading content about scientific matters. A few received the vague but ominous label of content that may not be suitable for all advertisers. The pattern was unmistakably clear. You could create a video confidently stating 3i/Atlas is definitely just a comet and mainstream science has it completely figured out. That content was fine, monetized, promoted, but suggest there might be genuine anomalies worth investigating? Suddenly your video becomes advertiser unfriendly. Facebook's approach was the most overtly aggressive. The platform's fact-checking system, operated by third-party verification organizations, started aggressively labeling 3i/Atlas content. Posts sharing the 4chan leak got slapped with missing context warnings. Claims about the trajectory anomalies were flagged as partly false, even when the posts were simply quoting Avi Loeb's published calculations verbatim. The fact-check articles offered reassurance. Space agencies confirm no threat from interstellar comet. Experts say unusual features likely natural processes. The subtext was unmistakably clear. Don't worry. Don't speculate. Trust the authorities. Move along. The timing felt coordinated across platforms. All of this ramped up within 48 hours of the ESA photo release, right when public frustration was peaking over the lack of quality images. It's the kind of pattern that makes conspiracy theorists feel vindicated and makes skeptics roll their eyes at perceived paranoia. Because here's the reality. Social media platforms suppress content constantly. Algorithms change. Engagement fluctuates. Fact-checkers flag misinformation. These represent normal platform operations, not necessarily evidence of coordinated censorship. Unless there's a pattern, unless it's all happening simultaneously, targeting one specific topic, right at the moment when public interest is highest and official answers are most conspicuously absent. Some creators started using coded language to avoid algorithmic suppression. Instead of 3i/Atlas, they'd say the visitor or the object. Instead of alien or extraterrestrial, they'd use non-terrestrial or anomalous. It resembled watching people develop a new vocabulary to discuss something the platforms didn't want discussed openly. The Streisand effect in real time. The more aggressively the content got suppressed, the more people assumed there was something genuinely worth hiding. The more aggressively fact-checkers pushed back, the less people trusted the official narrative. Every attempt to manage the conversation just amplified the suspicion that the conversation urgently needed to be managed. October 29th and 30th. Mark those dates with absolute attention. In less than 72 hours from this moment, 3i/Atlas will reach perihelion, its closest approach to our Sun. It will pass at a distance of approximately 202 million kilometers, positioned just inside the orbit of Mars. For a natural comet, this represents the moment of absolute truth. The intense solar radiation at that distance should cause dramatic outgassing, possibly even complete fragmentation. We've observed it happen before with other comets. They approach the Sun, the heat becomes excessive, and they break apart into pieces. Spectacular when it occurs. And if 3I/Atlas is just an ordinary chunk of ice and rock from another star system, that's exactly what should occur. But here's the critical problem. We won't be able to observe it. 3I/Atlas will be positioned on the opposite side of the Sun from Earth during its perihelion passage. Every ground-based telescope on our planet will be rendered useless. The object will be lost in the solar glare, completely hidden from observation during what should be its most active and revealing moment. Some observers are calling it unfortunate timing. Others see it as suspiciously convenient. If something wanted to perform actions without being watched by Earth-based observers, it couldn't select a better window. Avi Loeb has been explicit about what happens next. In his October 3rd blog post, published on the exact day of the Mars flyby, he laid out two scenarios with remarkable clarity. If 3I/Atlas is a natural comet, it may erupt in a flare of outgassing or break up into icy fragments soon. The sunlight will deposit gigawatts of power onto its surface. That energy must go somewhere. For ice and rock, it goes into vaporization, sublimation, possibly structural failure. But then Loeb added the alternative scenario. Alternatively, if it is technological, it may maneuver to benefit from the Sun's gravitational assist or release probes that could intercept Earth or other planets owing to its retrograde orbit opposite in direction to the motion of the planets around the Sun. Read that statement again carefully. Release probes that could intercept Earth. He's not discussing passive observation anymore. He's discussing active deployment. The retrograde orbit is absolutely key here. 3I/Atlas is moving opposite to the direction planets orbit the Sun. That means any probe it releases doesn't have to fight against planetary motion to reach us. It can simply drop into an intercept trajectory and let orbital mechanics perform the work. From behind the Sun, completely hidden from our view, it would be trivially easy to launch something toward Earth that wouldn't be detected until it was already close. Loeb went further in his analysis. He wrote, "When you look at the Sun in the coming weeks, keep in mind that 3I/Atlas is passing behind it. If 3I/Atlas will maneuver towards Earth when it reappears on the other side of the Sun, the financial markets may crash. Financial markets may crash. That's not metaphor. That's not hyperbole. He's suggesting that if this object demonstrates technological capability, if it actively alters course toward Earth after perihelion, the economic and social consequences would be immediate and severe. Stock markets respond to uncertainty. The uncertainty of a potentially hostile interstellar object actively changing its trajectory toward our planet would represent existential-level uncertainty. The timing of everything compounds the tension unbearably. The government shutdown means NASA is offline during the critical observation window. The best images from the Mars flyby remain unreleased. Amateur astronomers cannot observe the object for the next month because it's behind the Sun. Radio telescopes haven't checked for transmissions. We're flying blind into the most important moment of this entire encounter. And whether through incompetence or deliberate design, we've created a situation where we won't know what 3I/Atlas does at perihelion until it's already done it. There is one group watching with sophisticated equipment. The Galileo project, led by Loeb himself, operates 3 observatories. One in Massachusetts, one in Pennsylvania, one in Nevada. They're equipped with high-resolution cameras, infrared sensors, and radio receivers designed specifically to detect anomalous aerial phenomena. During late October and early November, all 3 observatories will be in maximum operational mode, monitoring the skies for anything unusual. If 3I/Atlas releases probes, if there's enhanced UAP activity correlated with its perihelion passage, the Galileo instruments might capture it. Might being the critically operative word. 3 observatories covering a minuscule fraction of Earth's sky. If something arrives and it avoids those specific observation zones, we'll miss it entirely. Early November. That's when 3I/Atlas will emerge from behind the Sun and become visible again from Earth-based observation. Ground-based telescopes will be able to track it once more. We'll observe whether it survived perihelion intact or broke apart under solar stress. We'll measure its trajectory with precision to determine if any course corrections occurred. And we'll finally know whether the past 4 months of speculation, conspiracy theories, and unanswered questions were justified or just collective hysteria over a completely natural interstellar visitor. If 3I/Atlas emerges on the same trajectory it entered with, if it shows clear signs of fragmentation or increased outgassing consistent with solar heating, if it behaves exactly like 2I/Borisov did during its solar approach in 2019, then the mystery is essentially solved. Natural comet. Unusual chemistry, granted. Statistically unlikely trajectory, acknowledged. But ultimately just an icy remnant from another star system passing through spacecraft, creating temporary warmth, oases of possibility in an otherwise frozen wasteland. The discovery in Bright Angel of relatively young rocks with potential biosignatures supports this intermittent habitability hypothesis. It suggests Mars might have had multiple opportunities for life to emerge, persist, or even re-emerge after periods of dormancy. On Earth, we have discovered microbial life in the most extreme environments imaginable, deep underground, in acidic hot springs, frozen in Antarctic ice for millions of years, thriving in radioactive waste. Life, once established, is remarkably resilient and adaptable. If it ever took hold on Mars, there is no reason to assume it completely vanished just because surface conditions deteriorated. It might still exist, dormant or active, in subsurface aquifers or deep cave systems where conditions remain stable. The implications of finding even fossilized microbial life on Mars would be staggering. It would mean that life emerged independently at least twice in our solar system alone, suggesting that the transition from chemistry to biology might be relatively common whenever the right conditions exist. It would fundamentally change the equation when we calculate how many civilizations might exist in our galaxy. Currently, we have a sample size of 1, Earth, making it impossible to know whether life is a cosmic fluke or a cosmic inevitability. A second data point, even extinct microbes on Mars, would begin to answer that question. And if we find that Martian life shares biochemical similarities with Earth life, the same DNA-RNA protein system, the same amino acids with the same handedness, it might suggest panspermia, the idea that life can spread between planets via meteorites. Mars and Earth have been exchanging rocks for billions of years, blasted into space by asteroid impacts. If microbial life hitched a ride on one of those rocks, we might all be Martians, descendants of organisms that originated on the red planet and colonized Earth when conditions there became unfavorable. Alternatively, if Martian life is fundamentally different from Earth life, using different biochemistry, different genetic molecules, different metabolic pathways, it would suggest that life can emerge through multiple independent pathways. That the chemistry of life is not unique but represents one solution among many to the problem of creating self-replicating, evolving systems. Either finding would revolutionize biology, astrobiology, philosophy, and our sense of place in the cosmos. But until we bring those samples back, until we can examine them with the full arsenal of analytical techniques available only in Earth-based laboratories, the question remains tantalizingly unresolved. The Sapphire Canyon sample sits sealed in its titanium tube, a messenger from ancient Mars carrying secrets that might redefine what it means to be alive in this universe. Meanwhile, the search for life continues beyond Mars. The next generation of space telescopes will analyze the atmospheres of exoplanets, looking for biosignature gases like oxygen and methane that might indicate biological activity. Future missions to Europa and Enceladus will sample the water plumes those moons eject into space, searching for organic molecules and other signs of life in the subsurface oceans. Astronomers are even beginning to consider whether advanced civilizations might leave technosignatures, artificial structures, or emissions detectable across interstellar distances. Megastructures like Dyson spheres, industrial pollution in planetary atmospheres, directed energy beams, waste heat from massive computational systems, all theoretical but potentially observable with sufficiently sensitive instruments. The search is broadening, becoming more sophisticated, driven by technologies that would have seemed like science fiction just decades ago. And as our instruments improve, so does our ability to understand the fundamental forces shaping reality itself. The quantum realm, where particles behave in ways that defy classical intuition, is yielding secrets that might transform not just technology but our comprehension of what the universe fundamentally is. The 24 entangled logical qubits created by Microsoft and Atom Computing represent more than just a technical milestone. They represent humanity's growing ability to manipulate reality at its most fundamental level, to harness quantum mechanics not just to observe nature but to build tools that operate according to principles most people still consider mysterious or even impossible. Entanglement, the phenomenon Einstein couldn't accept, is now being engineered deliberately, used as a resource for computation and potentially for communication. Quantum entanglement might one day enable perfectly secure communication networks. Quantum internet, where any attempt to eavesdrop immediately disrupts the quantum state, revealing the intrusion. It might enable distributed quantum computing, where multiple quantum processors work together on problems too large for any single machine. And in the more speculative realm, some physicists wonder whether entanglement might play a role in consciousness, in the way biological systems process information, in phenomena we don't yet understand. These are early days, and much of the speculation will likely prove wrong. But the fact that we're asking these questions, building these machines, testing these ideas, marks a transition point in human capability. We're no longer just passive observers of quantum mechanics. We're becoming quantum engineers. The same progression is happening with fusion energy. For decades, fusion was something that happened in stars and hydrogen bombs, but not in controlled terrestrial reactors. Now, with the West tokamak maintaining plasma for over 22 minutes and private companies like TAE Technologies achieving breakthrough simplifications in their reactor designs, fusion is transitioning from physics experiment to engineering challenge. The question is no longer whether we can achieve fusion, but whether we can make it practical, efficient, and economical. Every additional minute of plasma stability, every improvement in confinement efficiency, every reduction in complexity brings us closer to a world where energy is essentially limitless and clean. A world where the primary constraint on human activity is no longer energy availability but imagination and willingness to cooperate on large-scale projects. Imagine cities powered entirely by fusion reactors. No carbon emissions, no radioactive waste that lasts millennia, just the slow conversion of hydrogen isotopes into helium, releasing energy exactly as stars have done for billions of years. Imagine desalination plants turning seawater into fresh water at scales that could green deserts, making agriculture possible in regions currently too dry. Imagine industrial processes that are energy-intensive, like manufacturing steel, cement, or synthetic fuels, operating without contributing to climate change. Imagine electric vehicles charged from fusion-powered grids, making transportation carbon neutral. Imagine deep space missions powered by fusion propulsion, reducing travel times and making the outer solar system accessible. The cascading effects of abundant clean energy would touch every aspect of civilization, potentially solving some of humanity's most pressing challenges, while enabling projects we currently dismiss as too expensive or energy-intensive. But energy abundance also raises questions. Would it lead to greater equality, lifting billions out of poverty? Or would it concentrate power in the hands of those who control the technology? Would it reduce environmental destruction by eliminating the need for fossil fuels? Or would it enable even greater exploitation of natural resources? Technology amplifies human choices. It makes us more capable, but it doesn't automatically make us wiser or more just. The same fusion reactor that could power a city could, if weaponized, cause destruction. The same AI that maps brains and discovers drugs could be used for surveillance, manipulation, or autonomous weapons. The same quantum computers that might cure diseases could break encryption and compromise privacy. These are not reasons to reject technological progress, but they are reasons to approach it thoughtfully, with attention to ethics, governance, and the long-term consequences of our choices. History offers both encouragement and caution. The Industrial Revolution brought unprecedented prosperity, longer lifespans, greater mobility, and access to information. It also brought pollution, exploitation, inequality, and weapons of mass destruction. The digital revolution connected the world, democratized information, and enabled collaboration across distances. It also enabled mass surveillance, misinformation, and new forms of crime and conflict. Every transformative technology carries both promise and peril. The outcome depends on how we choose to use it, on the institutions we build to manage it, on the values we embed in its development and deployment. The scientists and engineers working on quantum computing, fusion energy, AI, and space exploration are aware of these dual possibilities. Many are actively engaged in conversations about responsible innovation, about how to maximize benefits while minimizing risks. Organizations like the Future of Life Institute, the Center for Humane Technology, and numerous university research centers focus on the ethical and societal implications of emerging technologies. Governments are beginning, slowly, to develop regulatory frameworks for AI, though the pace of regulation often lags behind the pace of innovation. International cooperation on issues like climate change, pandemic preparedness, and space governance demonstrates that humanity can sometimes coordinate on global challenges, though the record is mixed. What gives me hope, listening to these stories of scientific progress, is the underlying curiosity and ingenuity they represent. The researchers drilling cores on Mars, the engineers stabilizing fusion plasma, the physicists entangling qubits, the astronomers mapping distant planetary systems, they are driven by a desire to understand, to solve problems, to push boundaries. That impulse, the drive to explore and create, is one of humanity's most distinctive and valuable traits. It has taken us from caves to cities, from wondering about lights in the sky to walking on the moon, from counting on fingers to building quantum computers. And it continues, propelling us toward futures we can barely imagine. The breakthroughs of 2025, individually impressive, collectively suggest we are living through a period of accelerating change. Not in every field, not all at once, but in enough areas simultaneously that the cumulative effect feels transformative. Within a single year, we have seen progress in energy, computing, medicine, space exploration, and our understanding of the cosmos. The connections between these fields, the way advances in one enable progress in another, create a kind of positive feedback loop where innovation accelerates. Quantum computers help design better materials for fusion reactors. AI accelerates the analysis of data from Mars rovers and exoplanet surveys. Fusion energy could power the infrastructure needed for space colonization. Observations of distant planetary systems inform our theories about how our own solar system formed. Everything connects, creating a web of knowledge and capability that grows more intricate and powerful with each passing year. And yet, for all this progress, so much remains unknown. We don't know what dark matter is, or if it exists at all. We don't know whether the anomalies on Mars represent ancient life or just interesting chemistry. We don't know if fusion will be commercialized in 10 years or 30. We don't know how far AI can advance or what limits it might encounter. We don't know if quantum computers will revolutionize every field or remain specialized tools for specific applications. We don't know if we're alone in the universe or if life is common. The unknown is vast, far larger than the known, and that is wonderful. It means there are still discoveries to make, questions to answer, frontiers to explore. It means the story of science is far from finished. Every generation inherits the knowledge of previous generations and adds to it, standing on the shoulders of giants to see a little farther. The researchers of 2025 build on foundations laid by Einstein, Bohr, Curie, Hawking, Sagan, and countless others whose names might not be famous but whose work contributed essential pieces to our collective understanding. And future generations will build on what today's scientists discover, asking questions we haven't thought to ask yet, using tools we haven't invented, solving problems we don't yet know exist. This multi-generational conversation, this accumulation of knowledge and capability, is one of civilization's greatest achievements. It transcends individual lifetimes, connecting the past and future through a shared commitment to understanding reality as clearly and completely as possible. So when you hear about an asteroid passing unnoticed in the night, or a comet brightening toward its closest approach, or scientists drilling Martian rocks looking for ancient life, remember that these are not just isolated events. They are part of a larger story, a story about curiosity and capability, about reaching beyond our grasp and sometimes, remarkably, succeeding. A story that includes everyone who looks up at the night sky and wonders, everyone who asks questions and seeks answers, everyone who contributes, however small that contribution might seem, to the great project of understanding our universe and our place within it. Now, before we continue into the final sections, I want to make sure you're still here with me. If this exploration has opened your mind to possibilities, if you're thinking differently about the universe and humanity's role in it, do me a favor. Leave a like on this video right now. Seriously, it matters more than you think. The algorithm decides whether this reaches 10,000 people or 10 million based partly on that simple action. Subscribe if you haven't already, because we're living through history in real time, and I'll be here documenting every breakthrough, every discovery, every moment when the impossible becomes real. And comment below. Tell me which part of the story resonated most with you. Was it the quantum breakthrough? The fusion record? The Mars samples? The mysterious visitor in our October sky? Your voice matters. Your engagement keeps this investigation going. The fusion breakthrough at the West Tokamak in France deserves deeper examination because it represents convergence, the point where decades of theoretical physics, engineering innovation, and international cooperation produce tangible results that move us closer to practical application. 22 minutes and 17 seconds might not sound impressive compared to the billions of years the sun has been fusing hydrogen, but for a human-built machine attempting to replicate stellar conditions on Earth, it's extraordinary. The previous record was just over 17 minutes, achieved by China's East Tokamak in January 2025, meaning we saw two major milestones within months of each other. This rapid progress suggests we're approaching a critical threshold where steady-state operation becomes routine rather than exceptional. Steady-state operation is crucial because future fusion power plants can't afford to shut down and restart constantly. The reactor needs to run continuously, like a conventional power plant, providing reliable baseload electricity to the grid. Every additional minute of stable plasma represents progress toward that goal, demonstrating that the engineering challenges of managing extreme temperatures, magnetic field configurations, and plasma instabilities can be solved. The West reactor uses superconducting magnets cooled to near absolute zero to generate the powerful magnetic fields that confine the plasma. Those magnets must remain stable while the plasma just meters away reaches temperatures 3 times hotter than the sun's core. The engineering tolerances are extraordinary, the margin for error minimal. Yet the team achieved 22 minutes of controlled fusion, proving their systems work. But West is not alone in this race. Multiple approaches to fusion are being pursued simultaneously, each with different advantages and challenges. Tokamaks like West and East use magnetic confinement in a toroidal or donut-shaped chamber. Stellarators use twisted magnetic fields that are theoretically more stable but harder to build. Inertial confinement fusion, the approach used at the National Ignition Facility, uses powerful lasers to compress and heat fuel pellets until they fuse. Private companies are exploring even more exotic designs, field-reversed configurations, magnetic target fusion, magnetized liner inertial fusion. This diversity of approaches increases the probability that at least one will succeed in achieving practical net energy gain. TAE Technologies' breakthrough in creating and stabilizing field-reversed configuration plasma directly in the reactor's center is particularly significant because it simplifies the system, reducing cost and complexity. Previously, their approach required elaborate formation sections at either end of the machine, adding engineering challenges and expense. By eliminating that hardware and creating the plasma in situ using neutral beam injection, they've made their reactor design more elegant and potentially more scalable. Neutral beam injection works by accelerating hydrogen atoms to high speeds and then injecting them into the plasma. When those fast-moving atoms collide with plasma particles, they transfer energy, heating the plasma to fusion temperatures. It's like starting a fire by adding kindling rather than waiting for spontaneous combustion. The private fusion sector's expansion reflects growing confidence that fusion is achievable within realistic timeframes and budgets. Commonwealth Fusion Systems has raised over $2 billion to build Spark, their demonstration reactor near Boston. Helion has secured funding from investors including Peter Thiel and Sam Altman, with Altman's OpenAI signing a power purchase agreement to buy electricity from Helion's first commercial plant. General Fusion is building a demonstration plant in the UK with support from the British government. These companies aren't pursuing fusion as a science experiment. They're building businesses based on the expectation that fusion will become a commercially viable energy source within this decade or the next. That level of private investment suggests sophisticated analysis by venture capitalists and corporate strategists who believe fusion's time has finally arrived. The economic case for fusion is compelling despite the high upfront costs. Once operational, a fusion reactor's fuel costs would be negligible. Deuterium from seawater is essentially free, and lithium for breeding tritium is abundant and cheap. There's no fuel supply chain to disrupt, no geopolitical dependencies, no price volatility. The main costs would be construction, maintenance, and eventual decommissioning, similar to conventional power plants. Unlike fission reactors, fusion produces no long-lived radioactive waste. The reaction itself creates helium, an inert gas used in party balloons. The reactor walls become radioactive from neutron bombardment, but that radioactivity decays relatively quickly, on timescales of decades rather than millennia. Fusion reactors cannot melt down because the plasma is so tenuous that any disruption simply stops the reaction. There's no chain reaction to run away, no catastrophic failure mode. These safety and waste advantages make fusion politically easier to implement than fission. Public acceptance of nuclear power has been hampered by fears of accidents and concerns about waste disposal. Fusion largely eliminates both issues, potentially allowing deployment in locations where fission would face opposition. Urban areas could potentially host fusion plants without the extensive exclusion zones required for fission reactors. This could reduce transmission losses, making the overall energy system more efficient. But the most transformative aspect of fusion isn't just that it's clean and safe. It's the sheer abundance it promises. Fusion fuel is effectively limitless on human timescales. The deuterium in Earth's oceans could power civilization at current consumption rates for billions of years. Even accounting for massive growth in energy demand as developing nations industrialize and new energy-intensive technologies emerge, we would never run out. This abundance fundamentally changes the calculus for what's possible. Currently, energy scarcity constrains choices. Societies must balance energy consumption against cost and environmental impact, making trade-offs between economic growth and sustainability. Fusion removes that constraint. Energy becomes a non-limiting factor, like air or sunlight. And when a fundamental constraint is removed, cascading effects follow. Technologies that are currently too energy-intensive become viable. Processes like direct air capture of carbon dioxide, synthetic fuel production, large-scale desalination, all require substantial energy input. With abundant cheap electricity, they become practical tools for addressing climate change and resource scarcity. Industrial processes can be redesigned without energy cost as a primary constraint. Manufacturing could become far more energy-intensive if that energy is clean and cheap, enabling techniques currently considered wasteful or expensive. Transportation transforms when electricity is abundant. Electric vehicles become clearly superior to combustion engines not just environmentally but economically. Charging infrastructure can be built without worrying about grid capacity. Ships and aircraft might use synthetic fuels created by combining captured carbon dioxide with hydrogen produced via electrolysis, using fusion-powered electricity. These fuels would be carbon neutral, releasing only the CO2 that was captured to create them, and compatible with existing engines and distribution systems. Even space exploration benefits. Fusion propulsion systems could dramatically reduce travel times within the solar system. A fusion-powered spacecraft could reach Mars in weeks rather than months, making crewed missions more practical and safer. The moons of Jupiter and Saturn, currently years away, could be reached in months. The asteroid belt, a potential source of vast mineral resources, becomes accessible. But let's return from speculation to where we are now. Fusion is not yet practical. The reactors operate in experimental mode, achieving fusion but not yet producing more energy than they consume when you account for all the systems required to run them. The National Ignition Facility achieved fusion ignition, where the fusion reaction produced more energy than the lasers delivered to the fuel, but the lasers themselves required far more energy than they delivered. Net energy gain for the complete system, not just the fusion reaction, remains the critical milestone no one has definitively achieved. That milestone, called Q greater than 1 in fusion terminology, is what separates scientific demonstration from practical energy source. ITER, the massive international tokamak being built in France, is designed to achieve Q equals 10. Producing 10 times more fusion energy than the heating energy supplied to the plasma. If successful, ITER will demonstrate that magnetic confinement fusion can be a net energy source. But ITER won't begin full fusion operations until the 2030s, and it's a research facility, not a power plant. The first commercial fusion power plant will likely come from private companies or national programs building on ITER's results, probably in the late 2030s or 2040s unless one of the alternative approaches achieves breakthrough success sooner. This timeline means fusion will arrive too late to solve the immediate climate crisis. The critical window for reducing carbon emissions is the next decade, and fusion won't contribute significantly during that period. Existing technologies, renewables, energy storage, grid improvements, efficiency measures must carry the load. But for the second half of the century and beyond, fusion could transform the energy landscape, providing clean, abundant power for a global civilization of perhaps 10 billion people enjoying high living standards without destroying the planet. That's the promise. The reality will depend on thousands of decisions, technical and political, made over the coming decades. Engineering challenges must be solved, materials developed that can withstand neutron bombardment for years, tritium breeding demonstrated at commercial scales, plasma stability maintained not for minutes but for months. Regulatory frameworks must be established, investments secured, supply chains built. None of this is automatic. Every breakthrough requires sustained effort by talented people working on difficult problems. But the direction is clear, and the momentum is building. For the first time in decades, fusion feels genuinely within reach, close enough that serious people are investing serious money and building real hardware designed to operate as power plants, not just experiments. And while fusion promises abundant energy in the future, quantum computing promises to transform how we process information, solve problems, and understand complex systems. The 24 entangled logical qubits created by Microsoft and Atom Computing represent progress toward what's called fault-tolerant quantum computing, systems where errors are corrected faster than they accumulate, allowing arbitrarily long calculations. Current quantum computers, sometimes called NISQ devices for noisy intermediate-scale quantum, are limited by error rates. They can perform short calculations before errors overwhelm the result. Useful quantum computing requires either reducing error rates dramatically or implementing error correction schemes that use multiple physical qubits to create one logical qubit with much lower effective error rate. Microsoft and Atom Computing's achievement demonstrates the latter approach working at a scale approaching practical utility. 24 logical qubits isn't enough to run most of the quantum algorithms that promise revolutionary speedups. Those typically require hundreds or thousands of logical qubits, but it's a significant step along the roadmap to building such systems. The technical details matter here. Creating a logical qubit requires encoding information across multiple physical qubits using quantum error correcting codes. The physical qubits must be highly entangled, their quantum states linked so that errors can be detected and corrected by measuring certain properties without destroying the quantum information you're trying to preserve. This is extraordinarily difficult because measurement in quantum mechanics typically destroys superposition, collapsing the quantum state into a definite classical value. Special measurement techniques called syndrome measurements allow you to extract information about errors without learning the actual quantum state, preserving the calculation while fixing mistakes. The fact that this works, that you can maintain quantum coherence while actively correcting errors, is remarkable and counterintuitive. It's like editing a photograph while keeping your eyes closed, relying on indirect feedback to guide your changes. Quantum error correction is what makes scalable quantum computing possible. Without it, you hit fundamental limits where adding more qubits doesn't help because errors accumulate faster than you can perform useful calculations. With error correction, you can keep scaling, adding more logical qubits, running longer algorithms, solving bigger problems. The race to build useful quantum computers is global and competitive. China has demonstrated quantum supremacy, performing calculations that classical supercomputers cannot feasibly replicate, though the practical utility of those specific calculations is debatable. Google achieved a similar milestone with its Sycamore processor. IBM has built quantum systems available via cloud access, allowing researchers worldwide to experiment with quantum algorithms. Startups are exploring alternative physical implementations using photons, ions, neutral atoms, or topological states rather than superconducting circuits. Each approach has advantages. Superconducting qubits can be manufactured using existing semiconductor fabrication techniques. Trapped ions have naturally long coherence times. Photonic qubits can operate at room temperature. Topological qubits, if they can be built, would be inherently error-resistant. Nobody knows which approach will ultimately prove best, or whether different approaches will excel at different tasks, creating a heterogeneous quantum computing landscape similar to how classical computing uses different processors for different jobs. What's clear is that significant resources are being invested, progress is accelerating, and the applications are potentially transformative. Quantum computers could revolutionize drug discovery by simulating molecular interactions with unprecedented accuracy. Current drug development relies heavily on trial and error because we can't accurately predict how complex molecules will behave in biological systems. Quantum simulations could change that, allowing researchers to test thousands of candidate compounds virtually before synthesizing and testing the most promising ones experimentally. This could dramatically reduce the time and cost required to develop new medications. Materials science could similarly benefit, designing new materials with specific properties, stronger alloys, better batteries, more efficient catalysts, currently involves substantial experimentation. Quantum simulations of atomic and molecular systems could accelerate this process, potentially discovering materials that enable technologies we haven't imagined yet. Cryptography will be disrupted. Modern encryption relies on the difficulty of factoring large numbers or solving discrete logarithm problems, tasks that classical computers struggle with, but quantum computers could solve efficiently using algorithms like Shor's algorithm. This means that once sufficiently powerful quantum computers exist, much of current encrypted communication could theoretically be broken. Governments and organizations are already preparing for this post-quantum cryptography era, developing new encryption methods resistant to quantum attacks. Optimization problems, which appear everywhere from logistics to finance to machine learning, might be solved more efficiently using quantum algorithms. Quantum annealing, a specialized type of quantum computing already commercialized by companies like D-Wave, shows promise for certain optimization tasks. Machine learning might be enhanced by quantum algorithms that can process and find patterns in data more efficiently than classical approaches. And there are applications we probably haven't conceived yet, emergent uses that will become apparent only once the technology matures and people start experimenting with it. The history of technology is full of examples where the most transformative applications weren't predicted by the inventors. The internet was designed for military and academic communication, not social media and streaming video. Smartphones were phones with email, not platforms for ride-sharing and mobile banking. Quantum computers might similarly surprise us, enabling applications that seem obvious in retrospect but aren't evident now. But quantum computing also raises challenges. The same capability that enables beneficial simulations could be used for harmful purposes, designing biological weapons or optimizing surveillance systems. The concentration of power that comes with transformative technology creates risks that must be addressed through governance, transparency, and international cooperation. These are not abstract concerns. They are practical challenges that will shape whether these technologies serve humanity broadly or concentrate benefits and control in the hands of a few. History teaches us that technological transition periods are moments of both opportunity and vulnerability. The introduction of nuclear energy gave us both power plants and weapons capable of ending civilization. The internet connected the world and enabled unprecedented collaboration, but also created new vectors for conflict, crime, and control. Artificial intelligence is following a similar dual-path trajectory. Every powerful technology amplifies human intention, both beneficial and harmful. The outcome depends on the choices we make collectively, the institutions we build, the values we embed in development and deployment. And this brings us back to where we started, with a mysterious visitor in our cosmic neighborhood, with blurry photographs and missing data, with questions that remain tantalizingly unanswered. Whether 3I/Atlas is a natural comet or something more extraordinary, whether it represents a message from another civilization or just a chunk of ice from a distant star system, the story illustrates something fundamental about the human condition. We are curious beings. We see something we don't understand, and we can't help but investigate. We notice patterns, we ask questions, we build tools to extend our senses, and we refuse to accept easy answers when deeper mysteries remain. This curiosity, this relentless drive to understand, is what brought us down from the trees and out of the caves. It's what drove us to map the Earth, to sail across oceans toward unknown horizons, to split the atom, to decode DNA, to land on the moon, to send robots to Mars, to peer billions of years into the past using telescopes that detect the faint whispers of ancient starlight. And it's what drives us now, in October 2025, as we wait for an interstellar object to emerge from behind the sun, wondering what we'll see when it reappears, hoping for answers, prepared for more questions. Early November will bring clarity, one way or another. If 3I/Atlas emerges on its expected trajectory, showing signs of fragmentation or increased activity consistent with a natural comet heated by solar radiation, then the anomalies we've discussed become interesting footnotes, statistical outliers that turned out to have conventional explanations. The WOW signal connection becomes coincidence. The trajectory becomes the rare but not impossible low inclination case. The missing images become the product of bureaucratic delays during a government shutdown. Everything returns to normal, and the universe remains a place where humanity is likely alone, or at least unvisited. But if it doesn't, if something changes, if the trajectory shifts in ways that outgassing cannot explain, if radio telescopes detect signals, if the delayed images finally surface and show structures that challenge our understanding, then we enter a new chapter not just in astronomy but in human history. The implications would ripple outward, touching every aspect of civilization. Philosophy, religion, politics, economics, all would need to adapt to a reality where we are not alone, where intelligence exists beyond Earth, where something or someone has visited our solar system with intention and capability far beyond our own. That possibility, however remote, is worth taking seriously. Not with panic or unfounded speculation, but with clear-eyed assessment of evidence, careful analysis of data, and willingness to follow the trail wherever it leads. Science at its best is neither credulous nor closed-minded. It doesn't accept claims without evidence, but it doesn't reject evidence because it contradicts expectations. The history of science is filled with moments when observations forced us to abandon comfortable assumptions, heliocentrism over geocentrism, evolution over special creation, quantum mechanics over classical determinism, expanding universe over static cosmos. Each time, initial resistance gave way to acceptance as evidence accumulated and better explanations emerged. We may be living through another such moment, or we may simply be experiencing the pattern recognition and meaning-seeking tendencies that helped our ancestors survive but sometimes lead us to see significance in random coincidence. Time will tell. The beauty of science is that it provides mechanisms for distinguishing between these possibilities, experiments, observations, predictions, tests. Unlike belief systems based on faith or tradition, science updates itself in response to new information. It's self-correcting, though sometimes slowly and with resistance. So what should we do while we wait for answers? First, stay informed. Follow legitimate sources, scientists publishing in peer-reviewed journals, space agencies releasing official data, researchers explaining their methods and reasoning. Be skeptical of sensational claims that lack supporting evidence, but also be aware that absence of evidence is not always evidence of absence, especially when that absence might be due to data being withheld or observations being difficult to make. Second, support continued exploration. The missions that discover new worlds, the telescopes that reveal cosmic mysteries, the laboratories that push the boundaries of technology, all depend on funding and public support. Societies that invest in understanding the universe reap benefits not just in knowledge but in technological capabilities, economic opportunities, and inspiration for future generations. Third, think about what these developments mean for how we live. The fusion breakthrough promises abundant clean energy, but only if we choose to build the infrastructure and distribute the benefits equitably. Quantum computing promises to solve currently unsolvable problems, but only if we address the security and ethical challenges it creates. The search for life beyond Earth promises to answer ancient questions about our place in the cosmos, but only if we're willing to accept answers that might challenge comfortable assumptions. Every breakthrough carries responsibilities alongside possibilities. And finally, remember that you're part of this story, not as a passive observer but as a participant. The questions being asked by scientists today are the same questions humans have asked for millennia. What is the universe made of? How did it begin? How will it end? Are we alone? What is consciousness? What is life? What is real? These aren't just academic exercises. They're explorations of the deepest mysteries of existence, and the answers, when we find them, belong to all of us. They shape how we see ourselves, how we treat each other, what we consider possible, what we consider worth pursuing. The breakthroughs of 2025, from quantum entanglement to fusion plasma stability, from Martian samples to interstellar visitors, represent collective human achievement. Thousands of people working across decades, sharing knowledge, building on each other's insights, failing and trying again, gradually pushing back the boundary between known and unknown. That collaborative multigenerational effort is one of civilization's greatest accomplishments, perhaps the most distinctively human activity, the systematic accumulation of reliable knowledge about reality. So when you look up at the night sky, when you hear about discoveries from Mars or breakthroughs in fusion or mysteries in deep space, remember that you're witnessing history. The questions being answered now, the tools being built now, the knowledge being discovered now, will shape the world your children and grandchildren inherit. And the choices we make about how to use that knowledge, how to distribute its benefits, how to manage its risks, those choices are ours to make collectively through the institutions and processes we've created for making such decisions. The story of 3I/Atlas isn't finished. The story of fusion energy isn't finished. The story of quantum computing isn't finished. The story of the search for life beyond Earth isn't finished. These are ongoing narratives unfolding in real time, and we are living through the chapters being written right now. What comes next depends partly on scientific discovery, partly on engineering achievement, partly on political decisions, and partly on choices made by billions of individuals about what matters, what's worth pursuing, what kind of future we want to build. The cosmos is vast, ancient, and full of wonders we're only beginning to comprehend. In the span of a single human lifetime, we've gone from wondering whether other galaxies exist to photographing black holes and detecting gravitational waves. We've gone from discovering the first exoplanet to cataloging thousands and beginning to characterize their atmospheres. We've gone from splitting the atom to building quantum computers that manipulate reality at its most fundamental level. The pace of discovery is accelerating, driven by better tools, more collaboration, and accumulated knowledge that enables each generation to see farther than the last. And now, as October 2025 draws to a close, as 3I/Atlas passes behind the sun during its closest approach, hidden from our view during what might be its most revealing moment, we wait. We watch the skies. We prepare our instruments. We check our assumptions. And we wonder what we'll see when it emerges, whether the mystery will deepen or resolve, whether this visitor from beyond our solar system will prove to be exactly what we expected or something that forces us to expand our understanding of what's possible in this strange and beautiful universe we call home. The answer is coming, soon. And whatever that answer is, the questions that follow will drive us forward, deeper into mystery, closer to understanding, further into a cosmos that never stops surprising those brave enough to look closely and think carefully about what they see. If you've stayed with me through this entire journey, through quantum mysteries and fusion breakthroughs, through Martian discoveries and interstellar visitors, through questions that challenge everything we thought we knew, then you're exactly the kind of person this content was created for. Someone who doesn't just accept easy answers. Someone who wants to understand the universe in all its complexity and wonder. Before you go, I need you to do 3 things. First, hit that like button right now. I'm serious. That simple action tells the algorithm that this content matters, that real investigation deserves to reach more people. Second, subscribe to this channel and turn on notifications because when 3I/Atlas emerges from behind the sun in early November, when those delayed NASA images finally surface, when the next breakthrough happens, you'll want to be among the first to know. And third, leave a comment telling me what you think. Do you believe we're being told the complete truth about 3I/Atlas? What discovery from this video fascinated you most? Where are you watching from? Your comment matters more than you realize. It builds a community of people who care about truth, who value evidence, who refuse to accept comfortable lies when uncomfortable truths deserve investigation. Share this video with someone who needs to see it. Send it to that friend who's always asking questions about space, about science, about what's really happening behind the scenes. Post it on Reddit, on Twitter, on Facebook, wherever people gather to discuss ideas that matter. And for those of you who made it all the way to this final moment, comment Atlas revealed below so I know you watched the entire investigation. You're the real ones. You're the people who understand that some mysteries deserve 2.5 hours of your attention because the answers might change everything. The next video is already appearing on your screen. Click it. Continue this journey with me, because the story doesn't end here. The story never ends. There's always another mystery, another breakthrough, another question that needs answering. And I'll be here documenting every moment, investigating every anomaly, following every trail of evidence wherever it leads. Thank you for watching. Thank you for caring. Thank you for being part of this investigation. The truth is out there, and together we're going to find it. Until next time, keep looking up, keep asking questions, and never stop searching for answers.